This lecture is all about continuous probability distributions and how to find them by hand with raw data, which is a review of something we've already done, and mainly how to find probabilities of continuous variables when you don't have the raw data using z-scores and something called the unit normal table. So many business situations are not concerned with discrete variables that are restricted to whole numbers. So back when we were doing those discrete probability distributions, remember the variables that we had to have to use those had to be discrete variables. Well, that's not always the case in business situations. Sometimes measurements can take on any value. Or in other words, they're continuous variables, meaning that they can be a fraction or a decimal. So some examples, like measuring the weight of a randomly selected box of Cheez-It crackers. You could have a box that's exactly 16 ounces, or maybe 16.12 ounces, or 16.15 ounces, or any interval in between whole numbers. Another example of a continuous variable that you might see in a business situation, recording the flight time from Las Vegas to Ohio. It's about 4.5 hours. See how it's not just a whole number response. Another example, measuring the amount of time that a customer spends on the phone with some Comcast representative or Cox representative or something. Time spent on the phone with the customer. That can be any interval of time. It could be 32 minutes. It could be 32 minutes and 3 seconds, or an hour and 10 minutes, or just any interval in between whole numbers. So it's not a discrete variable. Now we're moving into continuous variables. You can also use the unit normal table for continuous probabilities whenever you have a situation where you maybe don't have a continuous variable, but you have a discrete variable that has a really, really large x associated with it, or when you haven't measured it across time or across units, so you can't use the Poisson distribution, or when you want to find probabilities in a situation where you just know the mean and the standard deviation for that variable. So this should be a review for you as far as looking at probabilities when you have access to the raw data. And just breaking this down, this would be a frequency distribution table. Here, this represents the value for x, or whatever the variable is. So let's say that we're looking at how many pizzas sold each day since the grand opening. And let's say that this restaurant's been open for 46 days. So this represents the number of pizzas sold. And then this column, the frequency column, represents how many days did we sell, for instance, 6 pizzas. So 2 days, we sold 6 pizzas. 2 days, we sold 5. 20 days, we only sold 2. And then you add all these days together, and that gives you the sample size, or in this case, the population size, because we're really only interested in how many days the restaurant has been open, and in this case, it's only been open for 46 days, for instance. So when you look at calculating probabilities, which remember is the same thing as a proportion, you just take the number of the specific outcome, how many times that specific outcome occurred, and divide it by the total number of outcomes that you measured. So to find the proportion of days that we sold 6 pizzas, or the probability of selling 6 pizzas based on this data, you just take 2, the number of days that 6 pizzas were sold, and divide it by the total number of days to get the probability or the proportion. And you just do that all the way down. And notice that whenever you add up all of the probabilities for all the possible outcomes, you will get 1 or something very close to it within rounding error. Remember, 1 represents absolute certainty. So for instance, we are absolutely certain that if we randomly selected any given day in this data set, that they would have sold between 0 and 6 pizzas, adding them all together. Or, if we put it into percent chance, you just take that probability, multiply it by 100. So we're here, we can say, the probability of selling 6 pizzas based on this data is 0.043. Or in other words, there's a 4.3% chance of selling 6 pizzas on any given day based on this data. Well, when you add all those together, you should get something close to 100% within rounding error. And that's because this represents 100% of the observations. So you can answer lots of questions when you put your data into a relative frequency distribution table like what you see here. So what is the probability of selling 4 pizzas on a particular day? Well, you can just find the probability in the table. look for 4 pizzas, 0.043. Or you can find the probability of selling 3 or fewer pizzas on a particular day. So you could look at this data set and think about it two ways. If you've already got the probabilities calculated, just add up all the probabilities for 3 or fewer pizzas. So 0.152 plus 0.435 plus 0.261 plus 0.022. Or you can just add up the frequencies related to those number of pizzas. So 7 plus 20 plus 12 plus 1, 3 or fewer pizzas, and then divide that by the total number of outcomes. You'll get the same answer. And remember, just as a review, this represents a cumulative percentage because it's 3 or fewer. So any X or fewer represents a cumulative percentage or a cumulative probability. And you should remember that that's the kind of information that was presented to you in the binomial and the Poisson distribution. Well, what if we want to flip this and say, what's the probability of selling more than 3 pizzas on a particular day? Well, you can just say 0.043 times 3, because 0.043 for 4, 5, and 6 pizzas, that's greater than 3. That happens 3 times. Take that, multiply it by 3, you get 0.129. Or you could have 0.043 plus 0.043 plus 0.043. Or you could go the frequency route and just say 2 plus 2 plus 2 divided by the total number of days, 6 divided by 46, and you get 0.130. Now you should also notice that you could have used the complement rule here, because remember, when you add up all the probabilities for all the possible outcomes, you get something close to 1. If we didn't have rounding error, it would be exactly 1. So you could have also found this, if it's not less than or equal to 3, then it's greater than 3. 1 minus 0.870 would have given you 0.130. One last example using raw data. What's the probability of selling 2 to 4 pizzas on a particular day? Well, you could say, okay, let's add the probabilities for between 2 and 4 pizzas. So 0.435 plus 0.152 plus 0.043 gives you 0.630. Or you could add the frequencies together. 20 plus 2 plus 20 plus 7 plus 2, 2 gives you 29. Divide that by 46, you get 0.630. And quickly, I want to point out that yes, these two are somewhat different, but that's just due to the rounding error associated with the fact that I only took these probabilities out to the thousandths place. So that's a review. That's when you actually have access to the raw data, and that's something that we did in Chapter 4. But when you don't have access to the raw data for a continuous variable that's normally distributed in the population, you can use Z-scores and the unit normal table to find probabilities for any range of X values and to find the X value corresponding to any given probability. But keep in mind that in order to use the unit normal table, which is something that I'll show you shortly, you need to have a normal distribution in your data. And luckily, most things in the population are normally distributed. And typically, when we're using the unit normal table, we're looking for probabilities associated with populations. Because if we have a sample, we more than likely have access to the raw data. So we can find the exact probability or proportion or percent chance based on the raw data. But when we're working with populations, typically we don't have access to the raw data. So we can use this unit normal table to find the probabilities in the population even when we don't have access to all the data for that population. So it's a really important and useful tool. So let's just quickly review the normal distribution. And this should be a review mostly from Chapter 3. So remember, in this class, I'm really not going to go over any other distributions. We're just going to focus on the normal distribution, again, because most continuous variables in the population are normally distributed. And just remember that the frequencies are along the y-axis, and then the scores are along the x-axis when you plot out any distribution. And the mean in the normal distribution is equal to the median. So 50% of scores are above the mean and 50% of scores are below the mean. The mean is also equal to the mode in the normal distribution because most of the scores pile up around the mean. And remember, the mode is equal to the most frequent score. Now, in the normal distribution, there are some extreme scores that are either on the high end or the low end, but they're really rare, meaning that they have a really low probability. Most scores fall around the mean. Now, Z-scores, remember, you take Z and that equals the actual score minus the population mean, or the sample mean if you're working with a sample, and divided by the standard deviation for the population, or if you're working for a sample for the sample. Because the z-score tells you how many standard deviations away is any given score, or x value, from the mean. So think about it. Well, how many points away is the score from the mean? And then divide that by standard deviation to put it in terms of how many standard deviations away the score is from the mean. So you think about the mean is being the most common score, and then the standard deviation is just telling you how spread out are the scores, or the average distance of all scores from that mean, from that most common score. Also keep in mind that if you calculate the z-score for the mean of all the scores, that z-score is always going to be 0. So when you plot out your distribution and you're thinking about z-scores, you can always know that the mean is going to have a z-score of 0. So think about it. If you have a score that's equal to the mean, then this value that you find here is going to be 0. And 0 divided by anything is just going to be 0. Because think about it. If the score is equal to the mean, how many standard deviations away is that score from the mean? 0 standard deviations away, because it is equal to the mean. So that's only one piece of information that the z-score tells you, in that it tells you how many standard deviations away a particular x value is from the mean. But it's also important to know, is that x value above or below the mean? So that's what the sign tells you. So if you have a positive value for z, that tells you that the score is above the mean. Or in other words, it's to the right of the mean in the distribution. Because remember, scores are plotted along the x-axis from lowest to highest, left to right. Well, if you have a z-score that's negative, then that means that the x value that that z-score represents is below the mean, or to the left of the mean in the distribution. One last thing about the normal distribution is that it is symmetrical, meaning that if you folded it in half down the middle, right at the mean, you would have a mirror image on either side. So, if you think about that, there aren't going to be any negative z values in the table that we're going to be working with. And that's because there's no need to have the negative values, because they would just be an exact replica. The probabilities would be an exact replica of the positive side of the distribution. And I'll show you some examples to show you how that pans out when you're actually working these problems out. But if you think about the unit normal or the normal distribution being symmetrical and the z-scores being a mirror image on either side, well, z of 2 and z of negative 2, those are both representing scores that are 2 standard deviations away from the mean. Or in other words, the same number of points away from the mean. It's just one would be below, one would be above the mean. So before I go on to show you how to use the z-scores and the unit normal table to find probabilities for any range of x values and to find the x value corresponding to any given probability, let's make sure that you understand how to plot the z-scores in a normal distribution. So this should be somewhat of a review for you guys. Remember, I said that the mean is equal to the mode in the normal distribution. So if you see, this is the high point, the most frequent score, that also represents this population mean of 35 points. So it's right there in the middle. And then the standard deviation is equal to 2.5. So in a normal distribution, the points of inflection, when it really starts to go down as far as becoming less frequent, that usually occurs right at 1 standard deviation above and 1 standard deviation below the mean. So 35 plus 1 standard deviation, 37.5. 35 minus 1 standard deviation, 32.5. So if you remember the empirical rule, which we're going to talk about here in a little bit, you would know that 68% of scores fall between 32.5 and 37.5, or within 1 standard deviation of the mean. So now that I've pointed all that out, I want you to try to figure out all of the z-scores that would correspond to all of these x values. Now you can start off by using this formula, but then, and remember this is in the numerator and then this is in the denominator, so you'll want to take x minus the mu, that whole value divided by the standard deviation. So start off using that formula, and then hopefully you'll see a pattern emerge that results in you not needing to use that formula anymore. So pause the video and give it a try. Okay, so let me demonstrate how this hopefully worked out for you when you solved this on your own. So remember earlier, I said that the z-score for the population mean, or the sample mean, whatever you're working with, is always going to be equal to 0. Because if you have a score that's 35, it's 0 standard deviations away from the mean of 35. So it's a good starting point right here. That's your z-score of 0. Now I'm going to start working up from there and calculate a couple of z-scores to get me started. So z is equal to x minus the mean divided by the standard deviation. Well, x, let's go 37.5 minus 35, the mean, divided by the standard deviation that's given to you of 2.5. 37.5 minus 35 gives you 2.5. Divide that by 2.5, and you end up with a z-score of 1. So let's go ahead and place that there. Now let's go up one more to 40. So z equals now 40, that's our new x value that we care about, minus the mean of 35 divided by 2.5. 40 minus 35 gives you 5 divided by 2.5, and you end up with 2. So 2. Well, I'm looking at this and I can see that each x value that's represented here is increasing by 1 standard deviation. So 35 plus 2.5, 37.5. 37.5 plus 2.5 gives you 40. And then I see that that pattern continues. 40 plus 2.5 gives you 42.5, and so on and so forth. And remember, the z-score tells you how many standard deviations away a score is from the mean. And these are positive z-scores because the x value is larger than the mean. And I can see that it's gradually increasing by 1 standard deviation each time. So I can just fill this in. 1, 2, 3, 4, 5, 6. So a score of 50 is 6 2.5s away from 35. And if you take 6 times 2.5, you'll find that it is 20 or 15, and 35 plus 15 gives you 50. Okay. Now, if we go the opposite direction, I can see that the same pattern is happening, but now 1 standard deviation is being subtracted as we go down the line. But just to make sure, let's go ahead and calculate one. So let's find the z-score for 32.5. So 32.5x minus the mean of 35 divided by 2.5. Well, you end up with negative 2.5 in the numerator divided by 2.5. And voila, negative 1, because 32.5 is 1 standard deviation, or 2.5 points below the mean. So negative 1, negative 2, negative 3, negative 4, negative 5, and negative 6. So I did this example just to refresh your memory of how the z-scores can be plotted in the normal distribution and how they are related to the x values and the mean and the standard deviation. So remember earlier I said that the normal distribution has most of the scores piling up around the mean, and then you have more extreme scores as you get further out into the distribution, meaning that less frequent scores occurring. So in this population, whatever we're measuring, if somebody had a score of 50, that would be a really rare score. It's way out in the tail end of the distribution. And when we start to use the unit normal table, you'll see that the probabilities associated with these scores become less and less as the z-score for those scores gets further away from 0. So here is the empirical rule, which is something that I've showed you in the past. And this just shows you how the normal distribution can be broken up into specific proportions or probabilities based on the mean and the standard deviation. So if you have any score within 1 standard deviation of the mean, there's a 68% chance of a score randomly being selected that's within 1 standard deviation of the mean. Or if you put it in terms of proportions, if you have a normal distribution, 68% of the scores fall within 1 standard deviation of the mean. So the majority of scores are within that 1 standard deviation of the mean. And that makes sense because remember, the standard deviation tells you the typical spread of scores from the mean. So most scores fall within one standard deviation. Then once you go out a little further to, 2 standard deviations away from the mean, above and below, see your z-scores here, you see that 95% of scores fall within 2 standard deviations of the mean. So that's why when you start to get to z-scores that are beyond 2 standard deviations away from the mean, those are extremely rare outcomes. So I want to show you how you can use the unit normal table, and I'm going to use the unit normal table initially to prove these properties. So a quick review of the unit normal table. The unit normal table can be used to find probabilities associated with specific x values by using z. So you'll have the x value given to you, something that you're interested in. You'll calculate the z-score for that using the formula that we just looked at, and then you'll use that z-score to go to the unit normal table and find the probability that you're interested in. Or you can go the inverse way. You can start off with a probability or proportion or a percentile, use the unit normal table to find the z associated with that probability, and then calculate x from z using this formula here, z times the standard deviation plus the mean. And as you'll see here in a little bit, there's 4 different columns in the unit normal table. So column A represents the z-scores, which just correspond to different positions along the normal distribution, so along the x-axis. So if you look at the unit normal table, you'll see that the A column says z, and there's several different z-scores in that column. Then B is the proportion in the body, which is just the larger portion of the graph. And you'll see that that's kind of represented here. It says, B, that's the larger section of the graph. So if you were looking for a score that had this z-score or lower, you'd be looking in the body. Whereas if you were looking for the proportion of scores with this z-score or higher, you'd be looking in the tail or the smaller part of the graph. Then if you're interested in, the mean to z, meaning that I want to know the proportion of scores between the mean and this specific score, then you would go to column D and look for mean to z. So in the slides and on your handout as well, you'll see that I just give you some examples of what would be in the body, what would be in the tail, and what would be between mean and z. So draw out the normal distribution here, just for example's sake. I usually split it up in terms of z-scores. We know that the mean's in the middle, and the z-score for that's always 0. This represents the top 50%, the bottom 50% of the distribution. It's split directly in half. It's symmetrical. So the z-scores corresponding to different positions, that would be like, a z-score of 0 or 1 or 2 or -1 or 2. Proportions in the body, so to the left of z equals +1. So just for example, if we had 1 and -1. To the left of z equals +1, so this would all be a body, it's a larger section. Or to the right of z equals -1, so all of this would be a body as well. Then proportion of scores in the tail. So to the right of z +1, so if we were over here, greater than 1, z-score of 1, that's a tail. Or to the left of z equals -1, or, less than a z-score of -1, that's a tail, the smaller portion. And the proportion between mean and z, that would be, from 0 to 1, or from -1 to 0, or any z-score to the mean. And I'll show you how to use this unit normal table to find all sorts of wonderful things. So first, let's start off by using the unit normal table to confirm the empirical rule. So I'm going to always start by drawing out what I'm looking for, because that helps you determine if you're wanting to look in a body or a tail or the mean to z. So this first one, the proportion of scores with a z-score greater than 2, or the probability of selecting a score with a z-score greater than 2. So that would look like this. I always plot my 0 in the middle, and a z-score of 2 would be somewhere around here. And greater than 2, shade that in. Now that's clearly a tail. It's the smaller portion of the graph. And then the next one is looking at a z-score less than or equal to -2. There's my 0. Let's put Z here. -2. Well, this is also a tail. It's the smaller portion of the graph. And remember before I said that there are no negative values in the unit normal table. And that's because the proportion of scores, or the probability of randomly selecting a score from this area of the distribution, is identical to that in this distribution. So above 2 or below -2. So when we go to the unit normal table and we look for, let's go to the unit normal table and look for a z-score of 2. So keep on scrolling, and we're looking in this column here, the z-score column. And there's our z-score of 2. And the proportion in the tail is 0.0228. 0.0228. So now let's go into here. And let's make this larger. And P equals 0.0228. P equals 0.0228. Both of those are tail with a z-score of 2 or -2, same difference. And that's roughly 2.5%. So the empirical rule is kind of rounding up those probabilities a little bit to make it, a nicer number, 2.5% instead of 2.28%, but it's roughly related to 25%. So if we took this and multiplied by 100, 2.28%. Same here. Now let's look for the probability of randomly selecting a score less than or equal to 2. Well, according to the empirical rule, 2.5% of scores are greater than 2. So if we do the flip side, kind of like the complement rule, and take 100% minus 2.5%, everything that's left less than or equal to 2 or not greater than 2, 97.5%. So if we drew that out in a graph, there's our 0 representing the mean and our z, less than or equal to 2. So here's 2, and less than or equal to 2 is all this here. So that is a body. So when we go back to the unit normal table, we'll still be looking for a z-score of 2, but we're going to look in the proportion in the body instead of the tail because we're looking at the larger part of the graph. Z-score of 2, proportion in the body, 0.9772. Or, roughly 97.5% or 97.72%. Okay, so again, the empirical rule tries to simplify things a little bit by working with numbers that we're more comfortable with. But overall, we're confirming those rough estimates of probabilities or proportions using the unit normal table. Let's do another example. So, looking for the probability of randomly selecting a score with a z-score between -1 and +1, or a score that's within 1 standard deviation of the mean, either on the high end or the low end. So according to the empirical rule, this is a 68% chance of happening, or 68% of the scores are within 1 standard deviation of the mean. So I'm going to start off by drawing my distribution, plotting my mean in the middle that has a z-score of 0, and then my -1 and my +1. So in this situation, I am looking for scores that are greater than -1 and less than or equal to +1. So that represents something that looks like this. Well, there's several ways that we could go about doing this. Let's first focus on probably the easiest way because we have 2 mean to z's, right? This would be a mean to z. This would be a mean to z. So we can find the proportion from the mean to a z of 1 and add that to the proportion between mean and a z of 1. And that'll give us that proportion in the middle. So let's look at the table. So first we need to find the z of 1. There it is. And the proportion between the mean and z is 0.3413. So this p is 0.3413, and so is that. So we can take 0.3413 plus 0.3413, and we end up with, let's see, 0.3413 times 2. Hey, 68.26. Close enough. 0.6826, which if you multiply that by 100, it'd be about 68%. Now, you could have also said, okay, well, what is the proportion in the body for z equals 1, and subtract the proportion in the tail? Because if you find the proportion in the body, that'll give you all of this. And we don't want all of this, we just want this part. So you can take the proportion in the body, all of this, minus what we don't want, so the proportion in the tail for this z of 1. So if we go and look at the table, we'll see that the proportion in the body is 0.8413, and the proportion in the tail is 0.1587. So let's go back to our picture here. And the point, so this would represent 0.8413, and then the 0.1587. 0.1587. So we can take the 0.8413, subtract the 0.1587, and you still end up with 0.6826. So no matter which route you go, you're going to end up with the same number. So as long as you can draw these out and think logically about the parts that you want to look at, you can really go about it any way that you want, and you're going to end up with the same answer. So now let's look at the probability of randomly selecting a score within 2 standard deviations of the mean, or the probability of randomly selecting a score with a z-score between -2 and +2, or the proportion of scores within 2 standard deviations of the mean. Many ways to think about that. All right, let's draw this out. My beautiful sketches here with our 0 in the middle. That's our z-scores, -2 and +2. Well, according to the empirical rule, 95% of scores should fall within 2 standard deviations of the mean. But let's go ahead and use the unit normal table to confirm that. So we need to find a z-score of 2. There it is. And the proportion between mean and z, 0.4772. So from here to here, 0.4772. And from here to here, same, 0.4772. Remember, it's symmetrical, so there's the same proportion of scores between a z-score of 0 and 2 and 0 and -2. So we can just take this 0.4772 plus 0.4772. So 0.4772 plus 0.4772, and you end up with 0.9544. 0.9544. Or if you multiply that by 100, roughly 95%. Now you can also go the body minus tail or body minus tail route, and you'll still get the same answer. So unfortunately, you usually don't have the z-score. Usually, if you're looking for probabilities, you're looking for the probabilities of specific x values or ranges of x values. So when you don't have the z-score, you have to calculate it based on x, and then you can use that z-score to go to the unit normal table. Because if you look at the unit normal table, you'll see that there are no x values. You have to calculate z-scores based on the mean and standard deviation for those x values. And that's why the z-scores are so useful. Not only do they allow you to compare scores from different distributions, but they standardize the distribution so that you can have predictable probabilities for any given score from any given distribution based on z. So information from the Department of Motor Vehicles suggests that the average age of drivers is 39.7 with a standard deviation of 12.5. And we're going to assume that this distribution is normal. So most drivers are around 39.7 years old, and most drivers are also within 12.5 years of 39.7. So what is the probability of randomly selecting a licensed driver who's older than 50 years old? So in this example, 50 is our x value that's given to us. So we are going from x to z to p. So z is like our bridge between x values and probabilities. So the first thing we need to do is calculate the z-score. So the z-score is equal to x minus the mean divided by the standard deviation. In this case, x is 50, the mean is 39.7, and the standard deviation is 12.5. Well, 50 minus 39.7 gives you 10.3. Divide that by the standard deviation of 12.5, and you end up with a z-score of 0.824. So if we draw this out, because we need to know if we're looking at a body or a tail, I'm going to put my x and my z values here. So the mean in terms of the raw score is 39.7. We know that has a z-score of 0. And we're looking for the probability of randomly selecting a licensed driver who's older than 50. So in this distribution, 50 would be roughly here. And we just found out that the z-score for that is 0.824. And older than 50 would look like this. So do you think this is a body or a tail? It's totally a tail. It's the smaller part of the distribution. So we had the z-score of 0.824, and we find that z-score in this table here. So 0.824. So 0.82 if we round to the hundreds place. And proportion in the tail, 0.2061. Remember, proportion in the tail, z-score of 0.84, I'm sorry, 0.82, 0.2061. So P equals 0.2061. So that's the probability of randomly selecting a licensed driver who's older than 50 years old. Or in other words, a 20.61% chance if you multiplied that by 100. Now with the same distribution, what's the probability of randomly selecting a driver who's 30 years old or younger? So if we draw this out, our x and our z's, the mean's in the middle. The population mean is still 39.7. The z-score for that is always going to be 0 for the population mean. And 30 years old or younger. So if we think about where this would fall in the distribution, it's less than 39.7. So 30 would be about here-ish. And 30 years old or younger, that would be a tail. So we're not going to find 30, the x value in the unit normal table, so we have to compute z based on that x value, the mean, and the standard deviation. So z is equal to x minus the mean divided by the standard deviation. So 30 minus 39.7 divided by 12.5. Well, 30 minus 39.7 gives you negative 9.7 divided by 12.5. And when you do that calculation, you get negative 0.776. Negative 0.776. Now remember, the unit normal table doesn't have values that are rounded to the thousandths place. So let's go ahead and turn this into negative 0.78. And that's the z that we want to look for in the table. Now, check it out. We have a negative z-score. And that should make sense because the score, the x value that we're interested in, is less than the mean. So negative z-score makes sense. So now let's go ahead and look at, remember we're trying to find the z-score of 0.78. 0.78, proportion in the tail, 0.2177. So P equals 0.2177. That's the proportion in the tail. So the probability of randomly selecting a driver who's 30 years old or younger, 0.2177. Let's do another example, make it a little bit more difficult. Now we want to see the probability of randomly selecting a driver between 35 and 45. So if we draw our distribution out, and I still do this to this day, even when I'm doing this on my own, because it really helps prevent mistakes. It's always good to draw things out. So in terms of years, 39.7 is the mean. And when we convert that into a z-score, it's 0. Between 35 and 45. So 35 is less than the mean, 45 is greater than the mean, and we're looking for everything in between here. Well, we need to calculate two different z-scores for each of these x values, and then the easiest way to go about this is just find the probability or proportion between mean and z for both of those z-scores and just add them together. But keep in mind, you could also find the proportion in the body for the z-score that you find for 45, subtract the proportion in the tail associated with the z-score for 35, or you could find the proportion in the body for a z-score associated with 35 and subtract the proportion in the tail for the z-score of 45. But I'm just going to go the easier route and do the mean to z. So we need to find the z-score for 35. Z equals x minus the mean divided by the standard deviation. The first x I care about, 35 minus 39.7 divided by 12.5. Well, 35 minus 39.7 gives you negative 4.7, still dividing by 12.5. And when you do that math, you end up with negative 0.376. Negative 0.376. Round that up to negative 0.38 for the unit normal table. So that's the first z-score that we care about. And again, it's a negative z-score because the x value that it corresponds to is less than the mean. Now let's find the z-score for 45. And I'm writing down my formula again just to keep myself organized and make sure I don't make any mistakes. So x is 45 in this case, minus the mean of 39.7, divided by the standard deviation of 12.5. 45 minus 39.7 gives you 5.3, divided by 12.5, and you end up with a z-score of 0.424. Or 0.42 when we go to the unit normal table. 0.42. And this z-score is positive because it's greater than the mean. It represents an x value that's greater than the mean. So let's go ahead and find the proportion for mean to z for 0.38 and 0.42. So we're looking for a z-score first of 0.38. So 0.38, mean to z, 0.1480. And we're going to add that, see, proportion between mean to z, to the proportion between mean to z for a z-score of 0.42, or 0.1628. So 0.1480 plus 0.1628. So the z-score of 0.42 has a mean to z, remember, of 0.1628. 0.1628. And then the proportion between the mean and z of 0.38 was equal to 0.1480. And 0.1480 plus 0.1628 gives you 0.3108. And that is your final answer. So 31.08% of drivers are between 35 and 45 years old. So here's another scenario with another example. So let's say that an internet toy retailer stocks a particular toy at this warehouse, and every week the retailer has to decide how many units to order or stock. So let's say that based on empirical probabilities and past calculations, they find that the weekly demand for the toy is about 2,500 units with a standard deviation of 300 units. So they expect that prediction to be off up to 300 units. So if the retailer has 2,750 units on hand at the start of the week, then what's the probability that the weekly demand will be greater than the inventory? So the inventory in this case, 2,750, that is the X that we care about. So remember, in order to find probabilities associated with X values, we first have to find the Z-score. So let's calculate the Z-score for our inventory here, using X minus the mean divided by standard deviation. Well, X, 2,750, minus the mean of 2,500, divided by the standard deviation of 300. Well, 2,750 minus 2,500 gives you 250, and 250 divided by 300 leaves you with a Z-score of 0.833. So, if we draw this out, ever so shoddily, our mean in terms of X values is 2,500. We know that has a Z-score of 0 because it's 0 standard deviations away from the mean if we have 2,500. And we're looking at 2,750. It's above the mean. We just found that the Z-score for that is 0.833. So we want to know, what is the probability that weekly demand will be greater than the inventory? So more than what we have. So that is a tail. So we need to go find the proportion in the tail for a Z-score of 0.833. So looking for the Z-score of 0.83, proportion in the tail, 0.2033. 0.2033. So we can tell that the probability that we won't have enough units, that our demand will be greater than our inventory, is 0.2033. Or in other words, there's a 20.33% chance that we will run out of units. We won't have enough to supply the demand. So here's another example. So if the retailer has 2,000 units at the start of the week, then what's the probability that the weekly demand will be greater than the inventory? So now we have the X value of 2,000. So our Z-score is going to be a little bit different. So X minus the mean divided by the standard deviation. X is 2,000 minus 2,500 divided by 300 units. So 2,000 minus 2,500 gives you negative 500 divided by 300, and you end up with a Z-score of negative 1.667, or negative 1.67 when we go to the table. Makes sense that we have a negative Z-score because 2,000 is less than our mean of 2,500. So if we draw this out, X values and Z-scores, we've got 2,500 in the middle, the Z-score of 0. 2,000 would be roughly here. And we know that it has a Z-score of negative 1.67. So what's the probability that the demand will be greater than the inventory? So now we're looking at a body because our inventory is much smaller than the mean, whereas before we had more than the mean, and so we were looking at a tail. It's going to be less likely to run out when you have more units, whereas if you have fewer units, it's going to be more likely to run out. You're going to have a higher probability or more of this distribution shaded in. It's going to be a body. So let's go ahead and find the probability associated with the Z-score of 1.67 in the body. So looking for 1.67 Z-score, proportion in the body with a 1.67 Z-score, 0.9525 is the probability that we're looking for. So P equals 0.9525. So when we have fewer units, the probability of running out is a lot higher. So we have a 95.25% chance of running out of units when we have 2,000 units. So now we're looking to see how likely it is that weekly demand will be less than or equal to the inventory. So in this case, we could either do the whole, we already know that the z-score for 2,000, we just calculated it, is negative 1.67. So we could go to the unit normal table and look for the proportion in the tail, because we're thinking that demand is going to be less than the inventory. So here's our z and our x value. Still looking for 2,000 negative 1.67 if we round it to match the table. But now we're looking at a tail less than or equal to the inventory. So we could use the complement rule because earlier we found this probability. So if you take 1, which represents the probability of any outcome, and subtract this, you're left with what's left, which would be this right here. So you could remember this was equal to, from before, 0.9525. So you could just take 1 minus 0.9525, and you get 0.0475 for your probability. Or you could go back to the unit normal table and look for the probability in the tail associated with a z-score of 1.67. You'll get the same answer. 1.67, tail, column C, 0.0475. Same answer that you had before. Okay, let's move on. So it's not always the case that you are going to be looking for probabilities associated with a range of x values. Sometimes you need to find the particular probability, or I'm sorry, you have to find the particular x value associated with a probability or proportion or percentile or however it's presented to you. So you can also use z-scores in the unit normal table to do this as well. So here's an example of one of those situations. So back to this, we're a retailer. We know that demand is about 2,500 units with a standard deviation of 300. So now the retailer wants to limit the probability of being out of stock to no more than 2.5% a week. So they're only willing to accept a 2.5% chance of running out. So the question would be, how many units should the warehouse stock to only have a 2.5% chance of running out? So this is a situation where we are starting with P. We need to calculate or use the unit normal table to find Z, and then use the z-score to calculate X. So in this case, P is, if we relate this to the percent, if we take 2.5%, divide it by 100 to get the probability, P is 0.025, which is just 2.5 divided by 100. Okay, so we are going to be looking for 0.025 as a probability in the table. We're no longer going to be looking for the z-score first to then find the probability. We're going to find the probability first and then use that to locate the z-score. So if we draw this out, here's our distribution, our x values and z values, 2,500 with a z of 0, and we need to find x that's related to no more than a 2.5% chance of running out of units. So if we think about, we want to have a low probability of running out of units, we're going to be looking at the high end of the distribution because we'll want to have more toys to have this really low probability of running out. So what we're really looking for is the x value that corresponds to P equals 0.25 in the tail to the right on the positive end of the distribution. So let's go to the unit normal table, find 0.025 in the tail, this is the tail, and then see what z-score that is so that we can then calculate x. Okay, so we're looking for 0.025 in the tail. So let's see, 0.025, and these are numeric order. They get smaller as you go. 0.025. Okay, well, luckily we actually have an exact 0.025. But if you have a situation where you can't find the exact probability, then you go with the z-score that corresponds to the probability that's closest to the one that you're looking for. And if you have a toss-up between two that are the exact same distance away from the one you're looking for, then you always go with the larger z-score. But in this case, we actually did find 0.025 in the tail. That's what we were looking for. 0.025, that gives us a z-score of 1.96. So we know that the z-score that we're interested in is 1.96. But remember, we're wanting to figure out how many units we need to have. So we're looking for x in this case, not the z-score. So we can find x by using the z-score, the mean, and the standard deviation. So we just found the z-score, 1.96. And let's go ahead and write down that formula. Z times standard deviation plus the mean. 1.96 is z, standard deviation is 300, and the mean is 2,500. And you have to be mindful when you do this, because if you're looking for a z-score that's over here, you have to keep in mind that it's a negative z-score, so that when you do your calculations, you'll end up in the x value that's less than the mean. But in this case, the z-score we're interested in is above the mean, so we'll leave it in positive form. So 1.96 times 300 gives you 588. Add that to the mean of 2,500. And we know that we need to have 3,088 toys to have a 2.5% chance of running out. So if I can fit it in here, 3,088 corresponds to that z-score of 1.96, which also corresponds to a probability of 0.025. So now let's say that the standard deviation increases from 300 to 500 units. Then how many more toys will we need to ensure that the probability of weekly demand exceeding inventory is no more than 2.5%? So my picture still looks the same as the one I already drew. The only difference is now we're going to have a different z-score because our standard deviation has changed. I'm sorry, different x value because our standard deviation has changed. So we still know that the z-score is 1.96 because we still are caring about the z-score that corresponds to p equals 0.025 in the tail. That hasn't changed. The only thing that's changed is our standard deviation. So when we do our x formula, our z times standard deviation plus the mean, we have z still 1.96 times the new standard deviation, 500, plus 2,500, which is the mean. Well, 1.96 times 500 gives you 980. 980 plus 2,500 gives you 3,480 toys. So, for this distribution with this larger standard deviation, 3,480 would correspond to a z-score of 1.96. Now think about it. Why is there such a difference between A and B? Well, there's more toys needed to have that 2.5% chance of the demand exceeding inventory because the demand is less consistent. So our margin of error in this case is about 500 units, whereas here it was only 300. So we have less consistent sales. So to ensure that we only have this low probability of our demand exceeding inventory, we need to have more toys because we're compensating for the fact that there's more variation in this distribution than there is here. So we're back to our drivers example using that same distribution that we were using earlier to find the percentages or proportions or percentiles, however you want to think about it. And now we are going to use a specific percentile to then find x. So we are still going from p, finding the z-score in the table and using that to calculate the x value that we're interested in. And in this case, x represents age. So 30th percentile, if we draw that out, remember 30th percentile represents the bottom 30%. So the bottom 30% would look roughly like this. And if we turn 30th percentile into a proportion, we have p equals 0.30. So remember, percentile tells you, if we're interested in which age represents the bottom 30% of the distribution, or what age represents an age that is equal to or above 30% of the scores, or that separates the bottom 30% of the distribution from the top 30% of the distribution. Okay, so what age is at the 30th percentile, or the bottom 30% of drivers? So this is clearly a tail. It's the smaller part of the graph. And let's go ahead and label our mean 39.7 in terms of age. We know its z-score is 0. So let's go ahead and find p equals 0.30 in the tail so that we can then find the z-score and then calculate x. So p equals 0.30 in the tail. Keep going. That's 0.03. We want 0.30. Okay, 0.30. Oh! Well, here we don't see an identical exact 0.30. We have two, one that's right above, one that's just below, and you have to do the math to figure out which one is closer. Well, this one is 0.0019 away from 0.30. This one is 0.0015 away from 0.30. So we're going to go with the z-score that corresponds to the proportion in the tail that's closest to the one we're looking for. So the z-score we want is 0.52. So let's go back to our example. 0.52 is the z-score. So it's not just 0.52 that's our z-score, but it's negative 0.52 because we're looking at the low end of the distribution. So we're going to calculate an x value that's less than the mean of 39.7. So now we've got our z-score, and we need to find x using our trusted formula, z times standard deviation plus the mean. Well, the z-score that we just found is negative 0.52. Standard deviation is 12.5 plus the mean of 39.7. Well, negative 0.52 times 12.5 gives you negative 6.5. Add that to the mean of 39.7, and negative 6.5 plus 39.7, which is just like saying 39.7 minus 6.5, gives you 33.2. So let's plug that into our pretty picture here. And that is our final value. Now, you don't have to draw these pictures, but again, it's very useful too. It helps a lot, and it can also help you catch mistakes, because if you did this calculation and you forgot that it was negative, you would have ended up with a value that's greater than the mean, and you would have plotted that here, and hopefully you would have recognized that something was wrong, because you shouldn't have values to the left of the mean in your distribution that are greater than the mean. So it makes sense that this is a value, an age, that's less than the mean, has a negative z-score, because it's at the low end of the distribution. Let's do another example. What age is at the 70th percentile for drivers? Or what age represents the beginning of the bottom 70% of the distribution? So 70% of drivers are younger than or the same age as some value that we're looking for. Let's draw our distribution again. 39.7 in the middle, z-score of 0. The bottom 70%, remember this is the top 50%, the bottom 50%, separated by the mean. So we start, this would be the bottom 50%, so about 20% into here. Let's go here, roughly. And we're looking for the x value that corresponds to the 70th percentile, or p equals 0.70 in the body. And looking at this, I know that I'm looking for a positive z-score, and then my x value is going to be greater than my mean. So first, we need to figure out what our z-score is. So what z-score corresponds to 0.70 in the body? Now you could also find the z-score that corresponds to 0.30 in the tail. Because remember, 1, all of this, minus 0.70 will give you what's left. You're going to come up with the same exact z-score either way you go. I usually just stick with the one that's related to what's given to me. So looking for p equals 0.70 in the body. And we find, okay, so this one's just below, this one's just above, and this one is technically closer. Remember how I said you could look for 0.30 in the tail like we did before? Because you can look at either one. This would also be closer there. So both of those tell you we're looking for a z-score of 0.52, just like we were doing before. Only now we're looking at positive 0.52 for our z-score. So if we go back, 30th percentile, bottom 30%, 0.30 in the tail, that gave you a z-score of 0.52. But we had to know it was negative 0.52 because it's to the left of the mean. You could have also found p equals 0.70 in the body. Either way you go, you're going to get the same answer, 0.52. You just have to be mindful, based on your picture, is it above or below the mean? So you know if you have a positive or a negative z-score. So now we need to figure out x. So what age is at the 70th percentile? Using our lovely formula, z is now positive 0.52 plus the standard deviation of 12.5, or sorry, times the standard deviation 12.5 plus the mean of 39.7. So we already found that 0.52 times 12.5 gives you 6.5, only last time it was negative 6.5, plus 39.7, and you end up with an age of 46.2. And this makes sense because we had a positive z-score, we're looking to the right of the distribution, to the right of the mean, and our x value is greater than our mean. Okay. Let's do another example. So what age range represents the middle 50% of drivers' ages? This one's pretty tough, but I'll break it down for you. So if we're looking at our distribution, keep on drawing it out, 39.7, z-score of 0 for the mean. The middle 50% looks roughly like this. Now there's several ways that you could go about doing this, but remember, the middle 50%, we have a symmetrical distribution, so half of that middle 50% will be right here. 50% divided by 2, slashing it in half would give you 25%, which is a p-value of 0.25, and that would be from the mean to z. Same here. Half of that middle 50%, or half of that 0.50, 0.25 here, 0.25 here as well. So you can find the z-score that corresponds to a p of 0.25 from the mean to z, take the positive version of that and the negative version of that, and then find your x-scores that correspond to those. So let's go ahead and go to the table and find p equals 0.25 between mean and z. Okay, proportion between the mean and z. So let's see. Oh, just below 0.25 and just above 0.25. So we look at this. This one is 0.0014 away. This one's 0.0017 away. So let's go ahead and go with the z-score corresponding to this proportion from mean to z, which is 0.67. Now remember, we're not just going to use 0.67, we're going to use both the positive and negative because we have one to the left and one that's to the right, but both are the equal distance away. So negative 0.67 and positive 0.67 z-scores. So let's go ahead and calculate our x values, because that's what we really care about. So the first one, let's go ahead and start with the low end, so the negative version. So z times standard deviation plus the mean. So negative 0.67 times the standard deviation of 12.5 plus the mean of 39.7. Well, 0.67 times 12.5 gives you negative 8.375. So negative 0.67 times 12.5, negative 8.375 plus 39.7, and you end up with 31.325. So roughly about, 31 and then 0.325 here, our low end. So this is the first x value. Now let's find the x that's greater than the mean, to the right. So 0.67, not the negative, but just positive 0.67 plus 12, or times 12.5 plus 39.7. So that equals positive 8.375 plus 39.7, and you end up with 48.075. 48.075 right here. So what age range represents the middle 50% of drivers? 31.325 to 48.075. And our final example. I give you lots of examples because I hope that it helps clarify how to do this in practice. Okay, so information from the Department of Motor Vehicles indicates the average age of licensed drivers is still 39.7, and our standard deviation is still 12.5. And now we want to look at what age are the youngest drivers in the top 50% of drivers' ages. So let's draw our distribution again. And 39.7 and 0. The top 50%. So remember, the mean separates the top 50% from the bottom 50%. So what age are the youngest drivers in the top 50% of the distribution? Well, I can look at this and already know that that is 39.7 because the mean is in the middle. It represents the midpoint, so 50% above, 50% below. Remember, the mean equals the median in the normal distribution. But I can confirm this with the unit normal table. So if I need to find my z-score associated with p equals 0.50 in, well, we don't have a body or a tail. So as you'll see in the distribution table, you'll find 0.50 in the body and the tail that are in the same row. Because it doesn't really matter in this case. There is no body or tail. This is the only time that will happen when you have an equal, 50%. So let's go ahead and go to the unit normal table and confirm that the z-score is indeed 0 for p equals 0.50 in the body or in the tail. Okay. Proportion of the body, 0.50. Proportion of the tail, 0.50. Between mean and z is nothing because there is nothing between the mean and the score that equals the mean. It's just the equal to it. And see how this adds up to 1? Well, all of these, if you add the tail and the body together, add up to 1. Because remember, the entire distribution, all possibilities, have a probability of 1. It's certain that you'll get one of those possibilities. So 0.50, 0.50, z-score of 0. That just confirms what we already knew. So if we wanted to go through and calculate this out, when we have z equals 0, x is equal to z times standard deviation plus the mean, just confirm that it is in fact 39.7. 0 times 12.5 plus 39.7 equals 0 plus 39.7, and we still have 39.7. All right, so I hope that you are feeling pretty confident about your ability to do these problems and that this helps you a lot with your homework, and we will go over everything in class as well.